All right, so let's we're going to work this problem. No, this is a separate problem. The boat is traveling 20 meters per second at 123 degrees relative to the water. The dog runs 12 meters per second at 64 degrees relative to the water. What is the velocity of the dog relative to the boat? No, we're not. But that's the beauty of it, we don't care. Because if, just like when we worked problems relative to the ground, did we assume the ground was still?
I didn't.
Well, we pretended it was, but did we care if it was?
No.
No, because the ground's not still, not relative to the sun, right? And so if everything is within that frame of reference moving together, then we can ignore how it's moving, which is the case with the water here. We don't care how the water is moving relative to the ground because the dog and the boat are all within the same, they're in the same boat, so to speak, as far as relative to the ground goes.
So if you're both relative to the water, you can't have an A, B, B, C, can you?
Well, let's see. Speaking of, let's identify.
Is the dog on the boat?
Yes, the dog's on the boat. Yeah.
Oh, he's on the boat. Okay, that's it.
Yeah, I know. Sorry, the dog's not swimming, right?
Yeah, I thought you were
Doggy paddling? No. What's this? 20 meters per second at 123 degrees.
That's going to be BC.
That's BC?
Yes. Stop trying to chicken.
Yes, it is. What's 12 meters per second at 64? Who? AC, yeah. And we're looking for AB. And I know that if I have the velocity of AB and I add it as a vector to the velocity of BC, then that will give me the velocity AC. Is our unknown isolated?
Yes.
No, because we're looking for AB. So to get AB by itself, we subtract BC. So it's the velocity of AC minus the velocity of BC. So now I'm ready to start drawing these vectors. Now, as I've warned you, you don't have to draw these exactly to scale, but the closer you draw in the scale, the least likely you are to make a stupid mistake. So I'm going to draw VAC first, and I get, what? 12 meters per second at 64 degrees. So, actually that's a little bit too steep. Let's bring it down a little bit. That's 12 meters per second at 64 degrees. And I'm just going to draw the horizontal just so I see what the reference is there. Now, I'm going to add what to AC? Negative BC, right? The opposite of vector BC. If I were to add BC itself, where would it go?
Upward.
Yeah, up and left, right? It would go like this, because that's 123 degrees. So I need it to be the opposite of that. Now, how do I get the opposite? What's the direction of the opposite?
Complete opposite. Do it 180.
Good. I'm going to switch it 180 degrees, which, by the way, is one of my big pet peeves, right? When somebody's talking about, oh, wow, they had a big life-changing experience, and they changed 360 degrees. Okay. Yeah, so they turn around and kept going the same direction. No. If you're going to make a change, you're going to go 180 degrees. So you're either going to add or subtract 180 degrees, whichever one keeps you still between 0 and 360, right? So in this case, if we try to subtract 180 degrees, we would go negative. So that's not what we need to do. We need to add 180 degrees. And we get 303, right? So if I take 123 degrees and I take the opposite, I get 303 degrees. So when I add the opposite, right, that negative sign means I have to add the opposite of BC, then I need to head off at 303 degrees. And so I'm going to draw this about like that, right? Almost double the other vector. 20 meters per second at 303 degrees. And again, I'm going to draw a horizontal, just for reference. What's that angle right there going to be? That's 57, right? It's 57 less than 380. I mean 360. Right?
Why does that matter? That's 57.
You'll see in a second. So that's BC. Now, what's unknown then is the sum of those two vectors. The vector sum starts where we started and ends where we ended up. So it looks like that. Now, at first glance, you might be tempted to say, oh, yeah, I can just do 12 squared plus 20 squared and take the square root of it, right? But it's not a right angle, right? We don't have a right triangle here. So there are other ways of doing this, right? Law of sines, law of cosines. But for right now, we're going to stick just with right triangle trigonometry. We'll come back to the other ways eventually. But for now, let's do it with right angles. If I want to know that red line, here's the easiest way to do it. This vector right here, this 12 meters per second at 64 degrees, what does that really mean? It means it's doing two things at once. It's going up and to the right. It's going north and east at the same time. So it would be helpful to me to know how much of that 12 is going up and how much of that 12 is going to the right. Right? So how am I going to do that? Well, this right here is 26 degrees. And so this green line, I can use finding which trig function. Good. Cosine of 26 degrees is equal to whatever that side is divided by 12. And when I do that, I get 12 times cosine 26 degrees, which is? Thank you. 10.8. So when I say it's going 12 meters per second at 64 degrees, that means it's going 10.8 meters per second up or north. At the same time, it's going east how much? Well, now I just use sine of 26 degrees is equal to that side divided by 12.
You're just trying like random lines.
I know. I knew you got that one. Go back.
Please.
Please. As we do.
This side's 12, right? If I want to know what this side is, because that's the part that's going to the right, I can use sine function because I know this angle and the hypotenuse, and I'm looking for the opposite. And I get 5.3. So what I'm saying when I say it's going 12 meters per second at 64 degrees is I'm saying it's going 10.8 meters per second north and 5.3 meters per second east at the same time. Now I'm just going to do the same thing with this second vector. I'm going to say, hey, it's moving east at the same time as it's moving south. How am I going to get how much east it's moving?
The 20 is 20 that green line?
Yeah, 20 is the hypotenuse.
Okay.
Dude, sine of 57 equals x over 20.
Well, that will give me what? This side or that side?
South.
Okay, so you want to do that one first? Fine. Sine of 57 degrees equals this side over 20. And so this side is equal to how much? 16.8. And then, how am I going to do this side, the other side? Cosine of 57 degrees equals this side over 20. Therefore, this side is 10.9. So you see what we've done? We've taken that vector that really is doing two things at once, and we're breaking it down into the two things it's doing. I'm saying how much of that moving is moving east, and how much of that moving is moving south.
Well, how does that help you, like, get closer if I know that reference?
I'm about to show you.
Well, I get it, because that side down to the right, to the south side of the right, is going to be 20 minus, or no, wait, it's going to be 16.8 minus 10.2.
Yes. Do I know the sides of this red rectangle now? I mean red triangle.
Yes.
This side is how much?
16.8 minus 10.8.
16.8 minus 10.8. So it's 6.
Because you take the...
Because I went up 10.8, but then I came down 16.8. What's the total change in the up and down direction? Down 6. And then what about this side? It's 16.2 because I went to the right 5.3 and I added to the right 10.9. Just like when you added your vectors for displacement, we're doing the same thing with velocity.
So you just have to make a square around it and just figure out what everything else is.
That's one approach, yes. Okay. So that gives me what? 17.3 meters per second. And now all I need is
What?
the direction. So let's call that angle theta.
16 over 2. Or
Tan
16.2 over 6.
the theta equals 16.2 over 6. That theta is who? 70. Therefore, what's the direction of our vector?
340.
At 340 degrees. Because we're at 270 and then we go 70 more. So the final answer is 17.3 meters per second at 340 degrees.
Yeah, our test's going to be like 5 problems long and we're not going to get it.